Yeah. Maybe, hopefully. True. True. All right. So we've started talking about this combined loading business, and we did 2 examples on that last time that we talked about this that both ended up with normal stress. When you have normal stress from multiple things, you can just add them. No big deal, because normal stress is normal stress. And now we're going to, today, with this example, we're going to start figuring out what happens when you have both normal and shear going on in the same structure because of the multiple loading. And the example that we have is a pipe with a connection and a wrench that we're going to turn. And we're going to first, always, what's the first part of the process? It's a free body diagram, or we've done this enough that maybe we can kind of fast forward, but the first part really is always doing the statics problem and figuring out the reactions. Because you have to know the reactions internal to it to know what kind of stresses and what the stress magnitudes are. So, we've got some details. We've got the cap on the pipe is being tightened by a force that's going downward on the wrench. The pipe is 2-inch PVC, which is a nominal, which actually means that it's this 2 and 2.375. Let me get my, let's be purple today. So outer diameter of blah, inner diameter of blah, and it's 100 pounds down on this PVC, which I have always thought, gee, that's going to pop that PVC. 100 pounds is a lot for some PVC. But lest I digress. So we know we're going to need some area properties with this. We are given OD and ID, and so we know we're going to be doing stresses. We know we're going to need a moment of inertia. This is one of the things that's provided on the exam, but we know that that guy is an outer minus an inner, and that's going to be 0.6657. And we have, what all is going on? We have one force. What kind of loading does this create in this structure? What all do we have going on? Yeah, shear, because it's a straight linear force. There is a torque, which means there's what kind? It's a torsional load. So we got that. We got torsional load. We got a shear load. And that's also going to translate into bending. So we got all sorts of stuff going on just from that one force. So if we've got bending, we know we're going to have normal stress due to that bending moment. If we have torsion, we know we're going to have what kind of stress? Yeah, that kind. Doorknob stress? It's shear, though. Shear stress. Yeah, if you've got a torsional load.
Shear, it's this shear.
Right, true, exactly. It's not this shear, it's this shear, yes. But we have this vertical, so we are also going to have regular shear this way as well because of the shear linear force. So we got a lot going on. If we look at this as if we've taken a hacksaw and we've chopped it off up here at the base connection, because this is essentially a cantilever, and you know that the worst case is going to be back at the connection point at the cantilever. So this is where I'm taking my section cut, and I'm now looking at it like that. I've taken the beam away, and I'm looking at that face at that connection point. So I know that I am going to have, I'll change color. I know that I have that shear force V, and that's downward, as a stress resultant back at the connection point. we also established that we're going to have bending moment downward, and that's about the axis of this other pipe. Okay? And so I can draw that one like this as a double arrow, and that's a downward. So that's my bending moment. And then what else do I have? What's that last one? It's a twist. It's the torsion, and that wrench is going this way. So it's a torque about this axis into the page. And I can draw that guy like that. And it's this away. And that's my torque. All right, now what are the magnitudes of those? I'm going to start with the shear because that one's easy. It's just 100 pounds. So this guy, and I'll go over here, V equals 100 pounds. Okay, how about the magnitude of my twist? What's the moment arm for the twisting? That's the 12-inch moment arm. So how big is that torsional moment? Is 100 pounds times my 12 inches, so 1,200 inch-pounds. And what about my bending moment? That's the 23-inch moment arm. It's the 100-pound force, but the 23-inch moment arm, so we got 2,300 inch-pounds. So those are my stress resultants back at the connection point. But we don't really care about stress resultants or the reactions. We care about stresses. So if we have these things going on in a structure, what kind of stresses do they make? So let's start with bending. Let's start with Ogren. We got a bending moment. How do we get a stress?
It's going to be negative MC over I.
Yeah. We want the max case. This is symmetric, so we can just say that our max is our plus or minus MC over I. All right? What's my C? Where's my neutral axis? It's symmetric. So my neutral axis is across the middle. So C is just half the outer diameter. Okay? So we know our bending moment is 2,300. We know our C is half the outer diameter. That outer diameter was 2.375, and we'll take half of that. And that moment of inertia we figured out a second ago was 6.657 inches to the fourth. So we have this guy is plus or minus 4,103 psi. Now, we've got to think about this in terms of the whole surface, or what's going on all the way across the cross-section. So what does that, if this is my cross-section, and I sort of come over here to plot, what kind of stress happens at the top? Okay, it's downward. So I've got tension at the top. I draw tension away from a cut face. So over here to the right of my profile, I'm drawing the stress distribution. And at the bottom I have compression, which I draw towards a cut face. And how much is in the middle, Stephanie? Stress in the middle? At the neutral axis? 0. How does it vary in between? Linearly. So that's my normal stress profile in the cross section. I got no normal stress in the middle. I have 4,103 psi tension here, 4,103 compression here. So if I think about it in terms of at noon on my structure, what do I got? I got plus 4103. What do I have at 9 o'clock? 0. What do I have here? Minus 4103. What do I got here? 0. So that's what's going on over the whole surface with respect to my normal stress due to the bending moment. And that's one of the things that we have to keep score on. What else is going on? We got torsion. What kind of stress, Mr. Beasley? If I twist on something, what do I get? Mm-hmm. How do I figure it out? That's the one. Okay, we figured out our I a second ago. A handy-dandy piece of trivia that I don't expect you to memorize is that J's are actually half of I's, or it's given on the back page of the test. It's pi over 32 outer diameter to the fourth minus inner diameter to the fourth. Or 2 times I. Did I say half? It's 2 times, not half. But what's my torque? My torque was 1,200, right? 1,200 inch-pounds. What's my C? It's the same. It's the same. It's a different quantity in that we're talking about just the distance from the center to any point on the outside because it's round, but it's the same value. So 2.375 over 2, and J is twice that, 1.3315 inches to the fourth, and that ends up being 1070 psi. All right, so what's going on all over the cross section here? Now this is on this face. So the normal stress, if I take my section away, normal stress is either pointed at you or pointed into this surface. But when I twist on it, it's shear, and it's parallel to that surface. So what's going on? What's my direction? How do I draw it? It's the same direction everywhere. It's just clockwise. Right. Normal stress, sigma, normal stress, shear stress along the face. So what would I say in an orthogonal sine sense, if I put it on a kind of global coordinate system, what would I say is going on at noon? I've got 1070 in the plus I direction, or in the that-away direction. What do I have at 3 o'clock? 1070 down, 1070 this way, 1070 up. So you can think about it in a tangent to the circle sense. Make sense? All right. What else we got going on? Ooh, this one gets a little messy. It's the linear shear, or we'll call it the transverse shear. It's from the V. How do we get that stress? VQ over IT. So that causes shear stress. We get it from VQ over IT. And this one is a little tricky geometrically. I don't know. I kind of like it because it makes you think about it in just a slightly different way. Let's go back up to. Do I have another? No, I don't. Okay, I'm going to put in some more space. Insert page. Need lots of space. All right. So if I have my whole cross-section, where do I know, if I have a shear force V, where is my worst case shear force because of it?
The center, right?
It's at the center.
Quadratic.
It's quadratic and it's at the neutral axis. So I know that my worst case is here along the neutral axis. How much is it noon? 0. How much is it 6 p.m.? 0. So I know my worst case is along this center line along the neutral axis. Okay? Because I know that, I know where I want to make my virtual cut to do my Q calculation. You want to, it's as if you're taking a hacksaw and slicing it in half and you're shearing it at that neutral axis location. So we have tau equals VQ over IT, but we need our Q. Q is an area property like area, like moment of inertia, like any of these other things. We can think about it in terms of the Q of the outside minus the Q of the stuff that's not there. Okay, so we can say that this is A prime y bar, of the outside minus A prime y bar of the inner part. All right. If I just think about the areas, I need basically the area of a rainbow. And I can do that by area of a hemisphere minus area of a little hemisphere. Not a hemisphere, semicircle. We're not doing volumes. But you're with me, right? All right. What's the area of a circle? Pi r squared, or pi over 4 diameter squared. So what's half of it? Pi over 8. OD squared and pi over 8 ID squared. Clever that. See, tricky ways to think of things. All right, what's y bar of a round thing? It's in the back of your statics book. I don't expect you to remember that one. It is, in fact, 2, so this is the area, and your y bar is, in fact, 2 over 3 pi times the diameter. Yeah, I just remembered that one. No. But I know where to go look for it. So 2/3, 2 over 3 pi times the diameter, and 2 over 3 pi times the inner diameter. And then I can multiply these two things together and string it all together in a big, ugly, messy mess that ends up giving us that Q is 0.3804 inches cubed. Yes. So that is from the neutral axis here is this quantity. No, is that quantity. But so multiply those products and subtract them, and you end up with Q of the top half of a pipe. It's a little convoluted, but.
Is y bar the centroid?
Yes. Y bar is the centroid location of the solid shape, the centroid location of the little shape, but when you do this product and subtract this product from this product, you get the resultant Q. Q is the moment of area property that you need to go into VQ over IT. It's the thing that's sort of like area that goes into this formula. We got this guy, that's 100. We just went through all sorts of geometric gymnastics to get that guy.
How much area is around the centroid?
Pardon me?
Is it like to get a grasp of Q, like what Q actually is it like how much stuff is around the centroid?
It is, I guess it's in conjunction with the thickness, it's an indicator of the resistance to shear. Like the moment of inertia is a resistance to bending. It's an indicator, like mass is a resistance to motion.
Right.
And inertia, moment of inertia I is resistance to bending. Moment of inertia J is resistance to twisting. That Q factor is an indicator of resistance to sideways shift.
Based on a geometry.
All three
Right.
of those kill me. I cannot wrap my head around them.
It's tough when you don't have something like you can physically pick up something heavy and say, okay, that's mass. That's more than the plastic. But yeah, no, I'm with you that it's, what does it really mean? And it's the resistance.
Because
Yeah.
I like, when, I don't know, one of the early lab reports I did, I like looked up ion in calculus, class.
Oh, I'm sorry.
And I was like really trying to understand what it was, and I was like, no.
Yeah. Things from a very abstract mathematical perspective make sense to a very small proportion of the population. Like, even if you take the population of, like, people at Walmart, you run into people that can think mathematically, it's going to be like this much. Even when you take the population of practicing engineers who really understand the mathematical stuff innately, it's still a pretty small proportion. It certainly was at the end of my undergraduate career before my head really started wrapping around the math. I went into school saying I hated math. I mean, I still say I hate arithmetic, but I do hate arithmetic because I'm terrible at it. But the calculus and the what all of these integrals and how it all fits together, it really didn't click until my first senior year in some of my advanced mechanical engineering classes when it was like, oh, okay, math does work. So if it hasn't clicked, hang on tight because you should be on the crux of it falling into place. Lest I digress. I usually digress. Okay, so we got that guy, we got that guy, we got that guy. Uh-oh. What is this guy? Remember your thickness?
Two pieces.
It's that much. It's that much. It's twice the wall thickness or just the outer diameter minus the inner diameter. So 2 times the wall. So that guy is 2x wall thickness, however you want to calculate it. But we got numbers for all of those things. We got 100 pounds. We got this 0.3804 we just got, and a 0.657 from before, and then I did it by outer minus inner, and we end up with a number that is 185. Okay, I knew I was going to need lots of space. So now what does that guy look like in profile? Uh-oh. Is that too microscopic to see? What does that guy look like in profile? So we had clockwise for the other one. We've got compression at the bottom and tension at the top for that guy. What does this guy look like? We've already said it's 0 here and here. 0 at the top and bottom. Tau equals 0. Tau equals 0. And it increases quadratically from here to the max here. And are they up? Are they down? Which way do they point? Do they point the same way? Think about the shear force.
The shear that we just know.
Mm-hmm.
Wouldn't they be going?
Oh, do they go this way? What's going on? It's parallel to this face, just like the torsional shear, but it's down everywhere. Now, it is also into the plane because we are dealing with real three-dimensional stuff, and if you remember on our little cube of material, if you have a shear on one face, you have to have that corresponding shear on the other face to keep it in equilibrium, and we'll get to another drawing that maybe makes that make a little more sense shortly. But primarily, we have to think about it on this face, and it's down everywhere, and the max is at the neutral axis. So that is tau equals 185 psi in both of those locations.
Why would it be up? Like across the face.
The reaction is upward, but the shear at the cut face is in the direction of the applied force. The reaction back at the pipe connection is up, but the shear force on the face is down.
And it's its max at the neutral.
And it's at a maximum at the neutral axis. Okay, so now this is a very zoomed in version of the same thing that you've got. And so essentially what I'm going to do now is summarize what's going on at 4 locations. I call it noon, 3 p.m. over there where you can't see it, 6 p.m. down there where you can't see it, and here. And I'm essentially going to take and blow up little chunks of material at each of these locations. And one over here looks like that. Okay, so again, that's pulling material, little squares of material out of each of these locations, and we're going to draw all of the stresses that are occurring at each of those locations, and we're going to start with bending stress, and I'm going to put the bending stress in purple. In purple. Okay. If that is the surface that's flat to the wall, those arrows are going to come away from this. What do I have up here at noon? Tensile or compressive? Up at noon.
Bending?
Yep. We've got tensile, so it looks like that. How big was that?
41 up
Okay. And that's our sigma. How much sigma, Cassiola, do I have over here on this one?
0.
Sigma equals 0. What do I got down here, Brogdon?
Negative 4103.
Yeah. Sigma equals 4103. And what do I have here, D'Agostino? Sigma equals 0. All right. Now I'm going to change color to happy blue for the torsional. Okay. What do I have at noon for torsional? What's my value? It's 1070. And which way do I draw it? Yep, I go that way. So that is 1070 tau. But this is where also going into the other surface, you have to have that corresponding shear on the other face. Okay, how about over here? It's going to be down. 6 o'clock? Hmm? 1070 which way? Yeah. Oh, I forgot my other one going that way. And that. And this guy is 1070 up. Okay, who do I have left to account for? My linear shear. We'll go with green for that. How much is up here at noon? 0. So tau equals 0 for linear. How about at 6 o'clock? All right, back here at 3 o'clock, 185 downward. And here on this other one, 185 down. So now, can I add 4103 and 1070? Absolutely not. Absolutely not. Can I add 1070 and 185? Absolutely. So I have a net larger shear stress on this side. So net shear of 1255 over here, and a net shear of 885 over here. So my worst case stress state for shear is this one. But what are these normal stresses? The normal stresses are 3.5 times bigger. So this is one reason that we can often ignore the contribution of a shear load, because the stress that you get from the bending moment ends up overshadowing things. Now, the next thing we're going to learn is how to account for when we have both, because we have a 1070 shear here and a 4103 normal, but we don't know how to account for that. But clearly, that has to be worse than if I had no shear and just the bending, because there's more than one thing going on. And that's the concept of principal stresses and stress transformation that we'll jump into. We may just get to start it today. So questions on that guy?
Steve said that there's a corresponding shear, and that's only for torque? That you have the corresponding...
On the other face?
Yeah.
No, it's, I guess I should draw little green ones.
Okay. Well,
Yeah.
that was
Yeah.
what I wanted to...
Yes. So I did not, I was incomplete in that I should, yes, anytime you have a shear, you have the corresponding associated shears on the other faces. Yeah. All right. ECU sign. Oh, I guess one of the notes, it is the text stuff that I often just kind of scroll past. It is useful to read that stuff. This is a note about like lug wrenches, and if you've got a single-sided wrench like that, it's putting way more load on it than if you have one of like tire irons that's like a plus. It doesn't give you that that same torsional load or the same stresses, because it's a couple as opposed to the unbalanced side offset force. So anyway, it's more safe for your pipe or your lug nut or your whatever if you don't put the stress like that. Anyway, all right, a sign. We have a sign, and the sign itself weighs 100 pounds, and it's got 60 inches by 36 inches, and it's on a pole. Pole is 4 inches with an inner diameter, or no, with 1/4 inch wall thickness. This is 72 inches, and the wind is blowing at 1.3 psi. All right, what all do we need to do? I think one of the first things that we need to do is establish a coordinate system so that we know how to connect all of our math to this thing. So I'm going to say this away is X, and the wind is blowing in Y. Again, this is basically a cantilever beam situation where the worst case scenario is going to be at the connection point. So we need to figure out what all is going on with this situation. So I guess we'll start with, what are the forces that are going to be acting? I'll do forces in red because they're dangerous. What all's going on?
The weight of the sun.
The weight of the thing, where does the weight of the thing act? Through the center of mass. We're going to assume that it's a homogeneous thing. So we have a force due to weight. And we've got the wind force.
That's what. How do you convert a velocity into a force? Other than moment, is it momentum?
Like, what PSI would a 40-mile-an-hour wind?
Yeah.
Yeah, it's an ugly fluids problem, and I don't like fluids, so ask the internet. But we already know this one is 1.3 psi, which you guys know how to deal with a distributed linear load, right? 8 pounds per inch or something. Well, to do this statics problem, this is basically a planar distributed load, pounds per square inch. So we're going to do the statics problem by figuring out the resultant. So multiplying by the area over which it acts to figure out the resultant force, which is also going to act through the center of mass. So this is force due to wind. So my weight force, we are told, is 100. And my wind force is 1.3 psi times the area, and the area is 60 by 36. So 1.3 times 60 times 36 is 2808 pounds. All right. What all kind of reactions is this scenario going to make? Which away? Like that. Okay, what do we call that? Bending about?
Y-axis.
Bending about Y. Okay, which force and which moment arm? Okay.
Yeah.
Okay, weight is the force, and what's the moment arm?
Halfway.
It's the location of the center of mass of the sign, so that's 30, right? So weight of the sign, and the moment arm is that far. So we know we're going to have, what have I done? There we go. So I'm going to draw my little picture of the hacked off connection point. And I know I'm going to have a moment about Y from the sign leaning over under its own weight. And we know that that would go that away. And how big is it? It is the force due to weight times 30 inches, which ends up being 3,000 inch pounds. All right. What else is going on? Okay, if the wind is blowing, it's going to try and twist it. What's the moment arm on that one?
30 again, isn't
It's the same 30. But what axis is that about? It's z, and which force is it? It's the wind force. So we have a moment about z, which can also be known as a torque, that is going to be the wind force times the 30. So moment about z equals the torque equals some bigger number. I don't know where that number is. Maybe I didn't do that number specifically.
It's 2808 for the win.
It is 28080.
It's 84, 240.
Oh, you're looking for the big number.
Yeah, there we go. 84 240. Like I said, I hate arithmetic. All right, what else we got going on?
Is there bending
Oh, wait.
from the wind?
The wind's going to try and flop it over that way. So what is that? It is bending. It's what? No, it's a moment about x. And that one is this away. And what is that one going to equal? That's going to equal the wind force times what's that moment arm?
What height is this?
72 plus half of that, 18. So 90. Did I do the math wrong?
87.
What?
72 plus 15?
18.
18, okay. 18.
Yeah, it's 30 tall, or it's 36 tall, not 30. So force of the wind times 90. So the moment about x is 252,720 inch-pounds. Is that it? That's 3 dimensions, but we ain't done yet. Let's go for some blue. Because we have linear forces going on as well. Which way? Oh, that didn't change, bugger. Why does it do this to me? Okay, so its own weight is a linear compressive load. There are only 6 possible reactions, 3 moments and 3 linear. We got one more. What is it? Yeah, it translates, it would want to shear off that way.
So we got into static root. Whatever it is indeterminate.
No.
No.
Oh.
So V equals the wind force. And the axial P equals the weight force. So that's everything that's going on. It is a lot. And I pity those of you who don't have multiple colors because that's just a whole lot going on. Okay. So how in the world do we... How in the world do we analyze all of this? We can simplify it slightly because of radial symmetry. Ooh, I need to talk fast. Slightly because of radial symmetry. These are vectors. Moments are vectors, forces are vectors, and because this is a round thing, we can simplify this moment x and moment y into a single worst case component. We don't even really care about the direction, but it does a Pythagorean sum. You can figure out that your M total, so do I have another page down here? Yes. So because of circular cross section, we can find a resultant of mx and my. So M total is just the Pythagorean sum, and that ends up being 252,740 inch pounds. Did I already write that number? I wrote that number. That's no. We're good. Now, how is it that that works? How is it that we don't care about the direction? I'm about to explain that because of the various magnitudes. How big is this shear force? V wind, or the F wind is how big? 2808. And how big is the axial force? This guy's only 100. Those are trivial in comparison to these other things that we've got going on. You can analyze them, you can do the math, but their contribution is going to be orders of magnitude smaller, so we can just throw it away. We can just throw it away. If the numbers aren't small in comparison, you may not be able to, but the other thing is, where is it, no matter what, where is the maximum shear value due to the linear shear force? It's always at the neutral axis. So it's always where the normal stress is at 0. So your worst case normal stress is where you have no shear. And your worst case shear stress is where you have no normal stress. So if your normal stress magnitude is bigger, you know the shear stress is never going to be your worst case scenario. So to say that in a different way, the stress tau due to V is also ignored because it is where sigma bend equals 0. All right, so what do we have left? We have a torsion and we have a single bending stress that we've gotten the resultant of our two bending moments. So how do we get bending stress? That's our plus or minus MC over I. Our resultant was 252,740. What's our C? It's half of our diameter, which was a 4-inch pole. I, pi over 64, outer diameter to the 4th minus inner diameter to the 4th. So we end up with a 97204 PSI. So that is my normal stress due to bending. What else do I have? I have shear due to torsion, which is a TC over J. And we figured out that that was 84,240. That same C, and this is twice as big, pi over 32, 4 to the 4th, minus 3.5 to the 4th, and that ends up being 16,199 PSI. So our critical stress state has some torsional some shear stress due to torsion, and it has normal stress due to bending. And if I draw my little chunk of stuff at the base, if I happen to draw the tensile one, we've got 97 to 100, and we've got 16 200 psi. And if I went to the other side, if that's my noon, if I go to the other side where I've got compressive force, it just swaps this arrow and the direction of that arrow. So I've got a shear and a compressive, or a shear and a tensile. If I go to the neutral axis, what do I have? Just a shear. Okay? Is that making sense? Because what does my torsional profile look like? Torsion is all the way around, and this is compression on one side, tension on the other, with 0. So either this location or this location are my worst case scenario. So that's how I know, because this side and this side only have my 2 torsional shears. And with that, we will transition into figuring out how to deal with shear and normal in the same thing. So actually skipping over pressure vessels for a minute and going into part 6 next time. But there's this little issue of an exam tomorrow.
Just a minor speed bump.
Just